Alright, so hopefully you guys were either here for the earlier parts of class or read and or watched our initial discussion about mass defect and binding energy. Right, so mass defect is the difference in mass between an assembled nucleus and when we have pulled all those individual protons and neutrons out, right, their mass actually increases. The energy that we put into pulling them out goes into mass. Right, so Elizabeth, you're welcome to pay attention again, but I'd rather you spend this time to try those two problems. So the mass defect is that difference in mass between the mass of the nucleus, which is lighter, and the mass of the individual nucleons, which is heavier. And then binding energy is that required energy to go in there and pluck all those nucleons out. And we can calculate that by using our mass energy equivalency statement, but the M is our mass defect. Hi.
Sorry, read it.
Okay, I'm sorry. Elizabeth, you got one, right? Great. All right. So for most of these problems, my approach is typically we're given the mass of the nucleus, and we are given that here and here. And then we need to use the info in the data booklet on, the data booklet has the mass of the single proton, the mass of the single neutron. We can use that to calculate the mass of our separated nucleons. So you guys are going to want your data booklet open to where it says page 1 at the bottom, right? Because we're going to need those masses. It's the page that has all the constants and stuff. All right, so for oxygen, right, we're given the mass of the nucleus, 15.994, 915 atomic mass units, and I want to convert that unit, right? We're trying to find the binding energy in mega electron volts, so I'm going to convert that to this weirdo unit that we like a lot called MeV per c squared. And there's a conversion factor right on the last line of the data booklet, right? 1 atomic mass unit equals, that tiny amount of a kilogram, and then the 931.5 MeV per c squared. So I'm going to go ahead and convert that before I do anything else. That we are going to be limited by the 4 significant digits in our conversion factor. All right, so the first step is go ahead and put the mass of the nucleus in MeV per c squared, and now we can calculate the mass of our solitary nucleons once we've plucked them in. So oxygen 16, right, has 8 protons, because every oxygen nucleus has 8 protons, and 8 neutrons, right, because we have the isotope that has a total mass number of 16. So I need to find the total mass of 8 single protons and 8 single neutrons, right? So I can look in the data booklet and see that a proton, single proton, has a mass of 938 MeV per c squared. And then the neutron is a little bit heavier than that. It's 940 MeV per c squared. And we did remind ourselves last time that IB does mistakenly consider this 0 significant, so both of these have 3 significant digits. All right. So this is the mass of these 16 things when they're together, right? This would represent their mass when they're apart. So let me go ahead and multiply out the 8s and then add them together, and we should be seeing that that's a greater mass than 14,899. Then we'll do a big long pause after this step. Alright, so I'm going to do a quick pause. I'm just going to do a lap around the room to see if anybody is totally stuck. Making progress on number one? Yeah, finished. Okay. What did you get? Yeah, other than significant digits, I got this.
So the c-squared cancel out, right?
Yes.
Okay.
Significant digits.
I ended up with one.
One significant? Okay.
Are we getting somewhere?
Is it conversion
Okay.
factor just
Sorry.
one?
Are we getting somewhere back here?
Wait, to get to this,
How are we doing?
how do you do it?
Alright, so
How do you get from this?
That's okay.
to
this
Somewhere? Okay.
one unify top mass is
Comcast, you're getting somewhere? Okay.
Okay.
All right, so any questions from you guys so far about finding the mass of our 16 isolated nucleons once we've plucked them out of the nucleus? Yes.
For significant digits.
Yes.
Maybe like 1.50.
No, I think this is significant because both of these should have 3 significant digits, right? Because these are exact. The 8s are exact. So it's these that have 3 significant digits, right? So when I multiply, these both have 3. But then when I add them, right? All I care about is that this is precise to the 10s, and this is also precise to the 10s. So I do think that this should be precise to the 10s. So I'm not going to round it yet, but 15,020 is what that part of the answer would be if I was stopping. All right, so the mass defect is the difference in mass between these two values, the difference between the mass when they're separated out of the nucleus and when they're in the nucleus. So I'm literally subtracting those two values from each other. So I'm getting like 120 mega electron volts per c squared. I'll do another slight pause, and then it'll take us about 5 seconds to finish that problem up. All right, so you guys, for number one, I got 500 mega electron volts. 500 mega electron
Because it's
volts.
going to be like precisely 10 times.
It is because, no, I was precise to the hundreds of places. Yeah.
Why is it only one?
Anybody need a quick pointer on number one before I go back to the
Why is
folks
it?
that were out?
Why is only one significant?
Why is only one significant digit? When I multiplied my protons and neutrons by 938 and by 940, right, these limit me, so these should only have 3 significant digits, right? So, and then I'm adding, so I'm precise to the hundreds place, because 3 significant digits means this is precise only to the hundreds, and here same thing, 3 significant digits means it's only precise to the hundreds. So when I add those, this is precise to the hundreds, and then when I subtract these, right, I can't be any more precise than the decimal place this one had. Yeah, it really helps to circle stuff in. All right, so you guys, questions about the mass defect, the difference in mass between the nucleus and the disassembled nucleons being 120 MeV per c squared. All right, so the reason that this is such a great unit of mass for us is that the binding energy, right, is the mass defect times c squared. All right, the mass defect is 120 MeV per c squared, right, and then we multiply that by c squared. C squared and the per c squared cancel each other out. We never have to put in our 3 times 10 to the 8th there, right? The c squared and the per c squared just totally cancel out. So our binding energy is 120 mega electron volts. And that is always going to be true. The mass defect in MeV per c squared and the binding energy in mega electron volts is the same answer, 100% of the time. Yeah, Jack.
So like, let's say we have the question that we're saying find the binding energy.
Yeah.
So would we still have to, after we found the mass defect, it would be good enough to say that's the binding energy? We have to like write E equals mc squared and really show all that? Just show
I think that in some mark schemes, I would so yes, I would expect to see something like this. Probably some mark schemes would allow you to immediately go from there to there. But you know what? If I'm the author of the question, I'm not allowing that for full credit. All right. Why don't you guys? Well, no. I'd like to do the third one. The gold one together. Does anybody need more time to process or finish copying anything down? Or any final questions about this one? All right. So the gold one's actually a little easier because the mass of the nucleus is already in. It's not in mega electron volts, but it's in giga electron volts per c squared. So we don't have to start off with that initial conversion that we did for oxygen. All right. So the mass of the nucleus is 183.4 giga electron volts per c squared. The rest of you guys, we did do the gold example in class last time, right? Or did we get to it? I think we did. I just don't really have a great record. I don't have a great memory of dealing with the giga electron volts per c squared.
Oh, I think, yeah, we did.
We did? All right. That was just a long time ago. I'm having a hard time remembering. All right, so that's the mass of the nucleus. Now, we need to know how many protons gold has, right? So periodic table would help us out with that. It's got to be somewhere around, what, 60, 70? 79? All right. So 79 protons. And then, oh boy, 118?
Yeah.
Was that right? 197 minus 79, is that 118? Great. All right. So I again go to my data booklet, I find the mass of the proton in mega electron volts per c squared, and same thing with the neutron. All right, why don't you guys proceed with that, and then I do want to get mine on the board, but why don't you go ahead and get ahead of me. Anybody have an answer to number 2? Cliff, what'd you get? 2,800 what?
30.
Oh, I got something close to that, but a little different. I got 2,810 and mega electron volt. Actually, MeV per c squared. And that one was harder, right? We did stuff in a different order.
I added stuff.
Did anybody need help from me on number 1? All right, I'm not gonna issue help for number 2 right now, but I will put mine in the back. You can come take a look at how I handled it. Maybe that will help. So go visit number 2 if you need to.
Take a look at it.
Oh, yeah.
Oh, well, that's significant digits. All right, so you guys, why don't we review it for a sec? So all I did so far was add up the mass of my 197 individual nucleons, and I didn't convert it into giga electron volts per c squared, but did you guys get something resembling that for the total mass? Yes? All right. So mega is 10 to the 6th, giga is just 10 to the 9th, so I'm just going to move this decimal point 3 places over to the left, which would be 185.022 giga electron volts per c squared. And that's actually only significant to the 1's place. So the mass defect would be that mass, right, minus the mass of the assembled nucleus. So I'm looking at a binding energy of 2 giga electron volts. Alright, so 2 trillion electron volts is the amount of energy I need to spend to pluck all of those nucleons out of that nucleus and get them apart. Good? Danielle, you good? Kelly, you okay? You good? Okay, good. Robbie, you good?